Look up, you see it, don't you? That silent, glowing orb hanging in the velvet blackness of space, the moon. It feels familiar, like an old friend in the night sky. But this old friend has a secret: violent, chaotic, explosive. Its origin story is one of the greatest unsolved mysteries in our solar system. We have clues, we have evidence. Before we had moon rocks, we had brilliant minds and powerful imaginations. One of the first big theories was the fission theory. It was proposed by George Darwin, the son of the famous Charles Darwin. He suggested the early Earth was a molten ball of rock spinning incredibly fast, so fast that a blob of material stretched out and broke off. That piece was flung into orbit to become the moon. Some romantically suggested the Pacific Ocean basin is the scar left behind. It's a great story, but it has a fatal flaw. The physics just doesn't work. To fling off something the size of the moon, the Earth would have had to spin much faster. Its day would have been only about 2.5 hours long. We have no evidence Earth ever spun that quickly. So, with apologies to George Darwin, the fission theory was put on the shelf. With the early theories failing to explain the evidence, science needed a new idea. And in 1975, a radical new hypothesis emerged that was both catastrophic and strangely beautiful. It's called the giant impact hypothesis, and it is the reigning champion of lunar formation theories. It suggests that about 4.5 billion years ago, our young Earth didn't have a moon. Instead, it had a cosmic sibling, another planet sharing a similar orbit. This planet, named Theia after the Greek Titan, was roughly the size of Mars, and it was on a collision course with Earth. Imagine the scene. Two young planets, both with molten surfaces and developing iron cores, hurtling toward each other. The impact was not a head-on smash. It was a glancing blow, but one of unimaginable power. The energy released would have been trillions of times greater than all the nuclear weapons on Earth combined. Theia was completely obliterated. A huge portion of Earth's mantle was vaporized and blasted into space. The real test for any lunar formation theory came when humanity did something incredible. We went to the moon. Between 1969 and 1972, the Apollo missions brought back 382 kilograms of material. These weren't just souvenirs, they were time capsules from another world. For the first time, we could analyze the moon's chemistry directly in our labs. One of the first major discoveries from the Apollo samples was what they lacked. The moon rocks were found to be extremely poor in what we call volatile elements: water, sodium, potassium, which vaporize at relatively low temperatures. The immense heat generated by the collision would have boiled away these volatile elements from the debris cloud, leaving the newly formed moon depleted in them. Another key finding was the discovery of a specific type of rock called anorthosite. The lunar highlands, the lighter-colored areas you can see from Earth, are composed almost entirely of this rock. Anorthosite is a low-density rock that would have floated to the top of a molten body like cream rising in milk. The widespread presence of anorthosite is powerful evidence that the moon was once covered by a global ocean of magma, hundreds of kilometers deep. By using radiometric dating techniques, scientists determined that the oldest moon rocks were about 4.4 to 4.5 billion years old. Just when scientists thought they had it all figured out, a new puzzle emerged. Every element, like oxygen, comes in different flavors called isotopes. They have the same number of protons but a different number of neutrons. Objects that form in different parts of the solar system have unique isotopic fingerprints. Rocks from Mars, for example, have a different oxygen isotope ratio than rocks from Earth. It's like a chemical passport that tells you where an object came from. So, scientists measured the isotopes in the moon rocks and compared them to Earth's. According to the giant impact hypothesis, the moon should be made of a mix of materials, mostly from Theia, a smaller part from Earth. But that's not what they found. To everyone's astonishment, they discovered that the Earth and the moon are isotopic twins. Their oxygen isotope fingerprints are virtually identical. This was a huge problem. How could the moon be made mostly of Theia, yet look exactly like Earth? Maybe the impact was much more violent than we first thought, powerful enough to completely vaporize and mix both the impactor and a large portion of Earth's mantle into a single, homogeneous cloud of vapor. The isotopic crisis forced scientists to get creative. Enter the synestia hypothesis. Proposed by Simon Locke and Sarah Stewart in 2017, this model suggests something even more dramatic than a simple collision. The term synestia comes from syn, meaning together, and Hestia, the goddess of the hearth. It describes a rapidly spinning, donut-shaped cloud of vaporized rock formed from the collision of two planet-sized bodies. In this scenario, the collision was so energetic it didn't just create a debris disk. It vaporized a huge portion of Earth and Theia, merging them into a single, massive synestia. This swirling cloud of molten rock would have been enormous, with its outer edge extending beyond the orbit of the modern-day Moon. The entire structure would rotate as one, with no solid surface, just a continuous gradient of hot gas around a dense central core. As the synestia gradually cooled over hundreds to thousands of years, droplets of molten rock would condense in the outer regions, like raindrops forming in a cloud. These rock raindrops would then begin to clump together under gravity, forming a proto-moon in the cooler outer torus. Because this lunar seed forms from vaporized Earth mantle material in the outer synestia, it naturally inherits Earth's isotopic fingerprint, elegantly solving the isotopic crisis. Eventually, the synestia cools and contracts back to a spherical Earth, leaving the newly formed Moon in orbit. This hypothesis is still being tested with sophisticated computer simulations and peer review. It shows how science refines ideas when evidence drives us back to the drawing board. The story of the Moon's birth might be even more strange and spectacular than we ever imagined. The Moon is full of strange and wonderful features that give us more clues about its dramatic past. One of its most interesting quirks is its asymmetry. The near side, the face we see, is dominated by large dark plains called Maria, vast ancient lava flows that filled giant impact basins. But the far side is almost entirely covered in craters and rugged highlands, with almost no Maria. When the Moon first formed, it was much closer to a still molten Earth, one side facing this furnace, the other left in the cold. This temperature difference produced a thinner near-side crust and a thicker far-side crust, changing how later impacts expressed themselves. Large asteroids could punch through the thin near-side crust, allowing magma to flood basins and form the Maria. On the far side, the crust was too thick for the same effect. Recent missions have discovered evidence of water ice trapped in permanently shadowed polar craters, some of the coldest places in the solar system. That ice likely arrived over eons, delivered by comets and asteroids and then trapped in deep freeze regions. And yes, the Moon has quakes. Apollo seismometers recorded thousands, from shallow impacts to deep moonquakes hundreds of kilometers below the surface. The far side of the Moon was a complete mystery until 1959, when Luna 3 swung around and sent back the first grainy images. What we saw was a world completely different from the familiar face we knew, rugged, ancient, and almost without Maria. One intriguing theory suggests Earth briefly had two moons, a large primary moon and a smaller companion perhaps 1,000 kilometers across. These would have shared an orbit for millions of years until orbital instability sent the smaller moon into a slow collision with the far side of the main moon. It would be a low-velocity accretionary collision, more like a cosmic pancake splat, piling crustal material onto one hemisphere. That could explain the thick far-side highlands without a single giant crater. China's Chang'e, 4 landed in the South Pole Aitken Basin and found mantle-like materials, ground truth that the basin punched through the crust. Data from missions like this help test whether the big splat or thermal asymmetry explains the dichotomy. Science explores multiple possibilities. So, why does this all matter? Why spend so much time trying to piece together a 4.5 billion-year-old cosmic collision? The answer is simple. Understanding the Moon's origin is fundamental to understanding our own. The giant impact that created the Moon was arguably the most significant event in Earth's geological history. It reshaped our planet, likely kick-started plate tectonics, and may have delivered ingredients needed for life. Its gravitational pull stabilizes Earth's wobble. Without it, axial tilt would vary wildly, causing catastrophic climate swings. The Moon creates the tides, stirring oceans and creating intertidal zones that may have helped life transition to land. The Moon is also a stepping stone. Polar ice could supply water, air, and rocket fuel for future missions. Ultimately, the quest to understand the Moon is driven by curiosity. We look up and ask, where did you come from? How did we get here?